Okay, so analyze in math and the word discuss in math, those are kind of bad words. If you see the word analyze, it means literally find out everything you can about that object. So if I give you a function, I say analyze it, that means you've got a lot to do. You've got to look at the domain and the range and the asymptotes and the holes and the intercepts and whatever, okay? Study the symmetry. Okay, find the end behavior. If I use the word discuss, that's the same meaning. So if you look at some of the problems in the book, it'll say discuss the following graph or analyze the function. Both of those mean the same thing. It means analyze ad nauseum and discuss till you're blue in the face. That's what they both mean, okay? So make sure you know that. It doesn't just mean, find the domain or something. All right, so there's a big, long process here, and let's just write down the steps or the checklist of things you'll need to do for each problem. So the first thing you need to do is find the domain. Find the domain. That's very important. Okay, the second thing is write the function in simplest form. Write the function in simplest form. That means if it can be reduced, then reduce it. Okay? The third step is identify the holes and vertical asymptotes. The fourth one is find the horizontal asymptote, or there might be a slant asymptote. On these particular problems that we're going to do from the textbook, you will never run into one of those cases where there's two HAs. That's not going to happen. Okay? But it can happen in other types of problems. So I will put an S at the end of this, although it will never happen to you in this textbook. All right. All right, now I need to, this stinks. All right, 3.5, we're writing out the steps to solving. Okay, find the domain, find the simplest form, identify holes and vertical asymptotes, find horizontals or slant asymptotes. There should only be one in this textbook. Okay, next skill is, or next step to do would be, determine the behavior of the function near the vertical asymptotes using limits. Okay? Okay, so we would write determine the parity. That just means oddness or evenness, okay? Oddness, evenness of the function to check for symmetry. Step 7, find the intercepts. So that's an easy thing. You just let x be 0 to find y, let y be 0 to find x. And then lastly, sketch. The truth is, I actually start sketching well before this step, because I like to kind of sketch as I go along. Every time I find an interesting feature on that graph, I'll draw it onto the graph. That's just my style. And you probably would do the same thing. Otherwise, you're going to have to save all your drawing until the end, and then you have to go back through all your work again. Okay? Also, don't take these too literally. Like, some of these steps don't apply to every problem. For example, I might give you a problem that's already in simplest form, so there's no reason to put it in simplest form. Or I might give you a problem that doesn't have parity, like there isn't any symmetry. You just showed that there's no symmetry. I'll show you how again in a minute. Also, after step 2, the order doesn't matter too much. It's more like a checklist. Make sure you do these things, but not necessarily do them in this order. I do think you should do steps 1 and 2 first and second. But after step 2, you can just sort of mix these up and do them in whatever order you want. Okay? Does that make sense? So it's a checklist after you get to step 2. All right, let's try a problem. All right, so first one I'm going to do is, I'm only doing 2 problems. That's all you really need. First one we're going to do is f of x is equal to x minus 1 over x squared minus 4. Okay? All right, so the first thing is to find the domain, right? So that's easy enough. And it's also very important. So what does finding the domain actually help us do? Like, why would we want to know the domain? Okay, it will help us with step 3 later. Why would you want to know where the forbidden values are? Yeah, you kind of want to know what not to draw, right? So part of knowing what to draw is to know where not to draw. And that's important. So it turns out it's the first thing you do, actually, on a problem like this. So you would actually just basically factor the denominator so you could tell where the roots are. Okay, so x cannot be negative 2. That's because there's an x plus 2. And x cannot be 2 because there's an x minus 2 on the bottom. So record that, and let's move on to writing it in simplest form. Now, this problem is already in simplest form. Okay? So already in simplest form. In other words, I don't see anything that can cancel. I don't see anything that cancels out at all. So we get to kind of skip step 2, see? Okay, the next step says to determine the holes and vertical asymptotes. Well, you're kind of off and running already on this. So look at the denominator and the numerator. Do you see any common factors? Like, is there like an x plus 2 on the top? Or is there an x minus 2 on the top like there is in the bottom? Do you see that at all? I don't see that at all. So that means there's no holes. Fair enough. Don't have to have a hole in a graph. So no holes. And the reason, there's no common factors, top and bottom. Okay, vertical asymptotes occur when the denominator is 0 and the top is not 0. So in other words, look now again at the denominator. Nothing was canceled out. That x plus 2 at the bottom means that negative 2 is a vertical asymptote. So vertical asymptote at x equals negative 2. And the same thing with this x minus 2. This means that x equals 2 is a vertical asymptote. Okay. So I told you that I would kind of sketch this as I went along, right? So I'm going to go ahead and start that process now. So I know that at negative 2 and at positive 2, I have a vertical asymptote. And I recently found my asymptote tool. Check this out. Oh, except I started in the wrong place. I could draw a dashed line just by dragging my pen. Pretty cool. They look kind of lame. Anyway, those are the vertical asymptotes. That's all I know so far. Let's go on and go back to the function. We've done steps 1, 2, and 3. The next says determine the horizontal and slant asymptotes. This is where the book and I differ. In the textbook, they'll teach you a nifty little trick to get to HA. It takes 2 seconds. I need you to know how to do it using a calculus limit, because nifty little tricks don't work every school year, and they won't work for you next year. So what I'm going to do is have you diverge from the book a little. To find the HA, you're going to do 2 limits for me. LIM x goes to infinity. And also LIM x goes to negative infinity. Okay? So we do this by thinking of spit in the ocean. Remember? So you're going to do these problems both by thinking of spitting in the ocean. So with the top there, the x and the 1, you're just asking which term has the larger larger absolute value, let's say if you plugged in x equals 1 million, is it a million or is it -1? Which one has the bigger value? Obviously million. So x is the dominating term in the top. And you can play the same game downstairs. X squared dominates over 4, right? It's much bigger than 4 is. So you would reduce this problem for me on your test. Please note how to show your work. This reduces to x over x squared, which reduces to 1 over x. And now you answer the question, as x gets huge, what happens to 1 over x?
It's small.
What do you mean by small, though? Because we've got to be specific.
Closer to 0.
Okay, so this is going to go to 0. 1 over a million, 1 over a billion, 1 over a trillion, 1 over Google. This is going to 0. Don't draw an arrow going to 0. Right equals 0 because lim equals 0 means y arrow 0. Okay, so I'll say it again. Lim x goes to infinity of f of x equals 0 means y arrow 0. These mean the same thing. But you don't want to use arrows and limits in the same work. So notice everything's equal signs. Okay, good. And now let's go down and do the green calculation. It's the same exact thing. You have the same exact oceans, the same exact reduction. Oh, this is a negative infinity now. Let me fix that real quick. This is a negative infinity. But it's the same exact reduction and the same exact conclusion. And it represents a horizontal asymptote at y equals 0. So the answer that we got from the lim question is the HA. So the HA is at y equals 0. Okay, so another thing I'd like you to do on your test is just label all the lines. Okay? So your graph contains the curve x equals 2. It has the graph x equals -2. It has the line y equals 0. They're all there. Okay? And there's one more little thing that we kind of glean from this right here. You see where it says 1 over x? This limit, the function x minus 1 over x minus 4 and 1 over x are not the same graph, okay? But when x is huge, spit in the ocean dictates that this function looks kind of like 1 over x. See? So if you happen to know what 1 over x looks like, and it's right here, you actually got the two arrowheads figured out already on the extreme sides of the graph. So what I'm saying is we also know one other little fact, that this comes down and this comes up. I know that because that's what 1 over x does. See? And my limit reduced to a limit of 1 over x. Okay, so that's a little subtlety, but those arrowheads are there because this limit reduced down to 1 over x. And these are the arrowheads for 1 over x, so it's the arrowheads for this graph too. Okay? Let's go on to the next step, which is to determine the behavior of the graph as x approaches the asymptotes. Okay, so we're going to use limits for this because we're trying to study a little calculus. So I'll do this step in purple to study the behavior near the VAs. Imagine being just slightly to the left side of the first vertical asymptote. So let's just look at x equals -2 first. Imagine being slightly on the left of that and slightly on the right of that. Like, where are the arrowheads? That's the question. Is there an arrowhead going down here, or is it up on the left side of this asymptote? Also, on the right side, is it an up arrow or a down arrow? That's important. So it's probably down on the left because you've already got this blue going here. But we're not going to assume that. We're going to do a limit calculation. So we're going to do a limit on the left of this one, and a limit on the right of this one, and a limit on the left of this one, and a limit on the right of that one. 4 limits, showing all my work so that I can see the behavior near the asymptotes. So let's go ahead and try it. First thing I want to do is study x equals -2, and I'm going to do both sides of it. So I'm going to go, what is the limit on the left side of -2? Well, this means plug in a number slightly less than -2 is what it means. So I'm going to use -2.1. In fact, I'll use negative 2.01, which is even closer. So I'll use negative 2.01 minus 1 and negative 2.01 squared minus 4. I don't really plan on solving this. I plan on just thinking about the result. I think the top is negative, and I think the bottom is positive. The top is negative 3.01. The bottom is clearly positive because you're going to get something slightly larger than 4 minus 4. My conclusion is that this yields a negative number. My conclusion after that is that this arrowhead is down. So I just got this arrowhead on the left side of x equals negative 2 using a limit. It's just like I thought it would be. I thought that would be there. Let's go to the other side of that same asymptote. So we're still at x is near negative 2, but now we're on the right side of it. So we put a little plus superscript, and we play the same game. This time I need a number slightly greater than negative 2. So I'm going to use negative 1.99. And I'm getting negative over negative, which is positive. I'm getting negative 2.99 on top, and something slightly negative on the bottom there. Something less than 4, take away 4. Okay, that tells me that I've got an up arrowhead on just on the other side of that asymptote. See? So now I'm done with my first VA. Okay, now let's take a look at the other vertical asymptote. That's over at x equals positive 2. All right, so limit as x goes to positive 2 from the left side. I would want to plug in like 1.9 or 1.99 if you want to be really close. Again, you don't care about the decimals so much, just the fact that the top is positive and the bottom is negative, making the ratio negative. So go ahead and draw the arrowhead that corresponds to saying that the limit to the left of 2 is negative infinity. Go ahead and draw the arrowhead. We just learned that this, which means the left side of 2, has a negative behavior. So you're going to draw an arrowhead either down here or up here. And by negative here, I mean negative infinity. Okay? Because the closer you get to 2, the more exaggerated this negative is. Okay, so arrow down. Arrow down. So that's right in here. And one more limit, that's limit on the right side of 2. Let's just use 2.01. 2.01 minus 1 is clearly positive. 2.01 squared minus 4 is slightly positive. And dividing by something that's very tiny and positive like that is going to give you a massive, huge positive number. So this is going to positive infinity. And we get our last arrowhead right here. Okay, I could have probably guessed where those arrowheads go, but it really would have been just that, a guess. Now I have verification for it. And this is what you need to show me on your test. Okay? Okay, are there any questions on how I showed my work for that? It's pretty important to me, even if other teachers don't care about it. I do, because I'm your BC teacher next year. So, at the very least, figure out where the arrowheads go and write these statements after the fact. If you must do it that way, then at least do it. You can just kind of do this work in your head. And then for the actual showing of your conclusions, you can write, this is negative infinity, and this is infinity, and this is negative infinity, and this is infinity. And then that justifies your arrowheads. All the calculus writing there would justify. Okay, next statement, or next step is to determine the symmetry. Now, we haven't done this in a very long time. Okay, we have not done this at all since chapter 2, so it's time to review that. I think you're going to find symmetry is very easy to learn this late in the year. It's really easy to learn. After all the transformations we've learned, it's very, very simple, really. So I will switch to, need a new color. Somebody say a color. Brown? I heard brown first. Okay, so to do the symmetry, what is that, like brick? Okay, I don't know. Looks like brick here. It looks like brown on the whiteboard there. Okay, so symmetry is really easy to understand if you understand reflection. Okay, so let's just rewind back to 3rd grade. In 3rd grade, you were given a picture like this, and you were told that there was a line of symmetry right down the middle. What does it really mean? Both sides are equal. Mirror image, right? All these little buzz phrases. But what it really means is that if you reflect that image, that pre-image, over that line, you can't tell the difference between the old and the new, right? So that's what symmetry is. It's a line where once you reflect, you can't tell it's been reflected. Well, we know how to reflect a graph, right? If you want to try to see if this graph has that same feature that the heart has, why not just flip it backwards, look at it again, and see if it looks the same? So it's all very simple. What you're going to do is find f of negative x. That's going to flip it backwards. Okay, so let's try it. What is f of negative x? It's negative x minus 1 over negative x squared minus 4. And here's what the question is. Is this the same function we started with? Is it the same? It is not the same. So here's our conclusion. Since f of negative x is not the same thing as f of x, flipping it backwards creates a new graph. That means there's certainly no y-axis symmetry. There is no y-axis symmetry. If there was y-axis symmetry, flipping it backwards, you couldn't tell that anyone had flipped it. All right, so we were saying there's no y-axis symmetry. Also, as you know, some graphs, let me get my pen going here again. Yeah. You know, some graphs, like this English letter N, right? The English letter N is interesting because if you flip it backwards, it doesn't look like an N anymore, it looks like this. But if you flip it upside down, you get the exact same result. Isn't that true? Isn't that true? If you flip it either over a vertical line, it looks backwards, right? Or if you flip it upside down, it looks exactly the same as when you flipped it backwards. See? So this is what we mean by an odd function. Isn't this kind of like a sine wave? See what I'm saying? So the sine wave has this feature. The sine wave, you can flip it backwards or upside down, you can't tell. It's exactly the same thing. In other words, f of negative x, grab my brown marker here, f of negative x is the same thing as negative f of x. See, long before we learned reflection, we were talking about this, but there was no context, like you might not have understood it. This is just simply saying that a backwards function matches the upside down function. See? Well, is that true for our graph? Is putting in a negative x the same thing as just multiplying by negative 1? Let's check. We already found f of negative x. Is that the same thing as just slapping a negative on the original function? Well, they might look kind of the same to you right now, but try plugging in 10, for example. You're going to get negative 11 over 96 equals negative 9 over 96. They're not the same. See? So our conclusion is that it's not one of these types of graphs. It doesn't have this neat origin symmetry, see? All right, so we would just say, since f of negative x is not the same thing as the opposite of f of x, there is no origin symmetry. Another way to say all this is that this function is neither even nor is it odd. It's neither. It also means when I sketch this function, I'm going to try really hard to make it so it doesn't really look symmetric. I don't want it to look symmetric. Okay, so I hope that the second time learning symmetry was very clear what it all means, because it's not that complicated, especially after you learn reflection. Okay, let's go back to this picture now, and also our instructions at the top. So we need to find the x-intercept and the y-intercept, and we also need to sketch it out. That should be pretty easy for us. Okay, so the x-intercepts, y-intercepts, I'll just do that in green. So the x-intercept, you set the y equal to 0. Now you should not need a calculator to solve that. Just look at it and tell me what value of x makes the top 0. 1, right. So x equals 1. It's the only number that would make this fraction 0. So 1, 0 is our x-intercept. And there's only one x-intercept, evidently. To find the y-intercept, you would actually make x 0. So you just get 1/4, of course. This is an old skill for us. So we're going to add these to our graph. We need a point at 1, 0, and we need a point at 0, 1/4. 1, 0, and 0, 1/4. All right. So 1, 0, 0, 1/4. We'll just make that 1. And now it's time to sketch. So you've already got everything you really need. Just go ahead and draw in the curves. So I will do green for my final curve. So I already know it looks like this. Right in here. In the middle, it looks like it might be an odd parity, but we had determined that it's not quite symmetric to the origin. And then this side looks like this. Okay, here's a question. How many times could the green graph theoretically cross the horizontal asymptote? Infinite number of times. Remember the wiggling that we showed earlier? In this graph, do we know whether or not this green graph ever touches the asymptote again? It doesn't. Why? Okay, he's saying that we said that this graph is sort of the role model for this graph way out on the sides, and 1/x never touches, therefore this graph won't. That's pretty good logic. It's almost completely convincing. Also, when y was 0, how many answers did we get in our work? That's important. Only 1, right? So back down here, when we made y 0 on this phase, we got exactly 1 answer. That means it will never happen again. So we don't have to worry about other crossings. Otherwise, you'd have more x-intercepts, see? So always think about how many answers you got and what that means. Okay, and then the second example has a slant asymptote, but we can go through it a lot faster because you're not learning it, you're just applying it, and it goes really fast, actually. I still want a tidy graph, and I want you to use graph paper on this assignment. Okay? All right, so my function this time is, I'll use r of x to emphasize that the problems we're doing are all polynomials on top and polynomials on the bottom. And they're called rational functions. Okay? So polynomial over polynomial. The one I'm picking is x squared plus 5x plus 4 over x minus 2. Okay, so the first thing to do is find the domain. That's actually pretty easy. So the domain x cannot be 2. Writing it in simplest form basically means factoring and reducing it if you can. But I don't see any way to really reduce this. You can factor the top, I suppose. But nothing cancels. So I guess we're already in simplest form. Determine the holes and the VAs. Holes are points that reduce out, but I don't see anything that cancels, so no holes. Vertical asymptotes are x values that remain in the denominator after reducing. Nothing reduced, so I guess x equals 2 is our vertical asymptote. Finding the horizontal or slant asymptote, that's a calculus question for us. So we're just going to do our quick limit as x goes to infinity. And using spit in the ocean, we determine that we have x squared over x. Like that. In other words, this is very silly, but our expression is x, and we're asking what happens to x when x gets big. What happens to x when x gets big?
It gets big.
It gets big, right? Just like who's buried in Grant's tomb?
I don't know.
Grant.
No, it kicks Bob.
We assume it's Grant. Okay, so let's do the other direction. So that would mean going way out to the left. So if you do the other direction, it's LIM x goes to negative infinity, x squared plus 5x plus 4 over x minus 2. Now our ocean terms are still these two. So we just end up with LIM x goes to negative infinity, x again, which goes to negative infinity. So I guess we didn't really get an HA. Oh well, that's okay. No HA. You're supposed to get a number, see? What you just got was end behavior. So we're not able to find an HA. Did we learn anything about the graph, though, from that? What? We learned the end behavior, yes. So we did get the end behavior from studying that limit. Okay, so if we're going to start sketching, we do know one thing. There's definitely an arrowhead here and here. See? All right, let's try a slant asymptote. So a slant asymptote is found only through long division or synthetic division if you get lucky. But I say let's just do long division, x minus 2, divide that into x squared plus 5x plus 4. And if you hate long division, join the club. But you actually don't even have to finish it. You just have to get the mx plus b part of your quotient, and then you get to stop. So let's just try it out here. How many times is x go to x squared? X times. Distribute this. X squared minus 2x. Subtract 7x. Bring down the plus 4 for good measure, even though I probably will never use it. Ask how many times does x go into 7x? That would be 7 times. And there is a remainder term. I think the remainder is 18 or something, but who cares? The truth is, our slant asymptote emerged as soon as we got the mx plus b part of this. Okay, so we got a slant asymptote at y equals x plus 7. Next thing to find is behavior of the graph near the VAs. Why don't we draw the VA? We never did it. We said we had a VA at 2. Let's go in here and put that in. We never drew it, so there it is. And we said there's a slant asymptote at x plus 7. Okay, so I'm going to go and label everything. I'm going to go and label all this stuff. So this is x equals 2. This is y equals x plus 7. I know there's an arrowhead sort of up here somewhere and one down here. All right, and we were going to check for the behavior near that asymptote. Okay, so let's do a left and a right side calculation on that x equals 2. Okay, so let's do behavior near VA. So let's do limit as x approaches 2 from the left. And I actually kind of like using the factored version for this step because I like to be able to do the calculations really fast. If I'm going to plug in 1.9, I would rather have it look like factored. Okay, so I'm going to plug in 1.9 and maybe even 1.99. Just real quick. Don't forget to write the LIM in front. You're supposed to write that. Okay, so I'm just going to do it mentally this time. I'm plugging in 1.9 for each x. So that's going to give me 5.9 times 2.9, which is clearly positive, divided by negative 0.1. So that's a negative denominator. So this is going to negative infinity. Okay, there's parentheses around this limit thing. So this is just going to go to negative infinity. You can tell. And then if you want to do the right side, LIM x goes to 2 plus. You can imagine plugging in like 2.1. Everything's going to be positive, top and bottom, everything. You're going to get 6.1 times 3.1 over 0.1, which is actually a rather large positive number. Okay. So this is going to infinity. And now we can conclude that we have a down arrow on the left and an up arrow on the right, which is kind of what I expected. Okay, and now if I just get my x and y-intercepts, I'm good. Let's try to do the x and y-intercepts without showing any work, because it's really easy to do. If you want to know your y-intercept, just pretend there are no x's in this problem, right? Just make x 0. So you would basically get what? 4 over negative 2, right? So imagine making all the x's 0, you would just get 4 over negative 2, which is negative 2. So we got the y-intercept just by looking. It's at 0, negative 2. So y-intercept 0, negative 2. It's 4 over negative 2. So we can plot that. And you can get the x-intercepts just by looking at the numerator of the simplest form. See this x plus 4 and this x plus 1? Those must be your x-intercepts, because negative 4 and negative 1 is what makes this come out to 0, see? Which means your y is 0. So negative 4, negative 1. So now I know that my curve looks like this. I've got all my arrowheads ready. I've got a few points. Okay, so this brings up one last little question. Does the curve ever touch the slant asymptote? Is that even possible for the curve to touch the slant asymptote? It's good questions. How could we check that? On the last test, I gave you a problem where you had to use your calculator and use the intersect feature to see if two things crossed. And to find where those two graphs crossed. Do you remember doing that? Yeah. You were given a log graph and a line, and you're supposed to see where they cross using the intersect feature of your calculator. Doesn't that mean that we could just set the blue curve equal to the black line to see if they touch? Let's try that. It's actually really easy to do. So I'm going to take the equation, which is the blue curve, and I'm going to set it equal to that black line. I'm going to take, x squared plus 5x plus 4 over x minus 2, and I'm going to set it equal to x plus 7 to see what happens. So let's see what happens. This is sort of just for fun. Does f of x cross the SA? That's the question. Well, let's take x squared plus 5x plus 4 over x minus 2 and literally set it equal to x plus 7 and solve it. If we get an answer, then evidently they cross. And we'll find out where. All right. So let's multiply both sides by x minus 2. And you get x squared plus 5x plus 4 equals x squared minus 5x, x squared plus 5x minus 14. And this is very interesting. The x squared cancels out, the 5x cancels out, and we get 4 equals negative 14. What does that mean? What does that mean? They don't cross. These will cross whenever 4 and negative 14 are the same number. In other words, never cross. So, no. No. Does that mean that no graph can ever cross the slant asymptote? I'm not saying that. I'm saying this problem yields no solution when you try that. See how you can always try stuff, right? Come up with your own questions about it. Analyze it further. Okay, those are mine. And then I want to say one little thing. None of the ones I did have holes in them. And I don't think many of the ones in the book do either. But if there is a hole, it's really easy to work with. It doesn't make the problem any harder at all. If there had been a hole, let's say at x equals 5, then there would have been an x minus 5 both here and here. The graph would look exactly like it does now, except out at x equals 5, there would be a little open hole. That's the only difference. Okay? So if there is an extra redundant factor here, all it does is just punch a tiny little hole in the graph. You would have canceled it out on step 2 after declaring your domain, and you would have come up with all the exact same word, exact same graph. You just have to remember to go back and put a little bubble at 5 instead of a closed point. Okay? So that's that. All right, so you guys can work. You have about 10 minutes. And I'm going to stop the video. And that assignment's due on Friday.